Hi, good afternoon, everyone. Sorry for not being able to present in person due to the visa issues. Thank you for attending our talk, and I'm happy to introduce our latest work against Java deserialization vulnerability, ODDFuzz, hunting Java deserialization gadget chain while structure well-directed Greybox fuzzing. And I'd like to thank the contributor from Yangzhou University and the group, Tsinghua University, and East China Normal University. They made a significant contribution to this work. First, a little introduction about us. I'm Bill He from and Group Security at Gadget, and I'm also a speaker at Black Hat USA last year. And my colleague Howen is the founder of Cyber Utopia. I'm going to begin my presentation by providing a little background on deserialization gadget chains. Next, I will introduce the state-of-the-art solution that can be used to handle gadget chains automatically, as well as discuss the challenges that currently exist with these tools. Following that, we will present our approach, ODDFuzz, detailing its design and implementation, and explaining how ODDFuzz partially addresses the automation challenges. Then, we share our evaluation of ODDFuzz, first in terms of reproducing known gadgets and discovering new gadget chains. We will also conduct a detailed case study to demonstrate how ODDFuzz has assisted us in identifying 0 days. To conclude, we will highlight a few key points that deserve attention. Serialization and deserialization are features present in many programming languages. Serialization allows for the conversion of objects in memory into a stream of bytes. These bytes can be stored in memory, databases, and files. Its counterpart, deserialization, reconstructs an object from a serialized byte stream. This mechanism is very useful in many scenarios, such as RPC, persistence, and cross-process data transmission. But how do deserialization vulnerabilities occur? In Java, when an object of a class is deserialized and constructed, some magic methods in this class are automatically invoked, such as the readObject and the readResolve method. As shown in the slide code, when an evil object is deserialized, its readObject method is automatically executed, and this method executes a shell command. If an attack can control the byte stream being deserialized, this can lead to a Java deserialization vulnerability. However, in practical situations, things can become more complex. The code on the slide is a simplified version of a deserialization vulnerability in reality. Generally speaking, magic methods do not directly call security-sensitive methods. For instance, in the example on the slide, the readObject method calls some regular method, but due to the dynamic features in Java language, such as polymorphism, the method it may directly or indirectly call are numerous, and among them, it may call some security-sensitive methods. We refer to a call chain that starts with the magic method and ends with the security-sensitive method as a gadget chain, with the magic method refers to as the source method and the security method as the sink method. Why is the automatic discovery of gadget chains so important? For defenders, deserialization is unavoidable in many situations, most commonly in RPC scenarios. And in large companies, replacing native Java deserialization with a simple deserialization mechanism, such as the protobuf, is not an overnight process. Therefore, defenders need to mitigate deserialization vulnerabilities using a gadget blacklist, which need to be constantly updated as new gadget chains are discovered. For attacks, a Java deserialization vulnerability is only exploitable if a gadget chain is found. Attackers need to continually discover new gadget chains to bypass the defender's blacklist. Therefore, deserialization gadget chains are extremely important. If gadget chains can be discovered automatically, it holds significant implications for both attackers and defenders. There are some available solutions that can be used to hunt for gadget chains automatically. The first solution was mentioned is Gadget Inspect, which was proposed at the Black Hat USA 2018. It is a purely static solution. First, it uses symbolic execution to extract the relationships between the method paraments and the return values, as well as the relationships between the method paraments and the parament of the core state within it, and then storing this in summaries. Then it uses a breadth-first search to search for available deserialization gadget chains. However, due to its inadequate handling of polymorphism in Java and some inherent flaws in purely static solution, gadget chains has a higher rate of both positive and false negatives. Furthermore, it requires manual inspection of the reports. Serial hybrid was proposed at ASC 2020. It employs points to analyze to construct the heap access path from source object to sink object, and utilize fuzzing to generate actual injection object for verification. However, its heavyweight points analysis may not be applicable to large applications, causing it to be unable to complete some baseline cases within the given time. In addition, injection objects may have a multi-level class hierarchy. Fuzzy solutions that has not been specifically designed about such a complex structure are ineffective. CodeQL is a semantic code analysis engine provided by GitHub. As the slide shows, it extracts the summaries from the code base and stores them in a snapshot databases. Users can then leverage its DSL language to create a custom query rule. CodeQL exists these queries and generate results, while CodeQL offers a fully custom query interface and support virus language. Its effectiveness is wholly dependent on the quality of the user-defined queries. And as a purely static solution, the result it generates require manual verification, which can be a potential drawback. In summary, state-of-the-art solution faces the following challenges. Firstly, runtime polymorphism and other dynamic language features in Java make it difficult to strike a balance between precision and recall. This is a common issue faced in Java programming language APIs. Secondly, Java deserialization gadget chains can be quite long, which not only result in large computational space, but also amplifies inaccuracy. Lastly, existing tools lack of the capability to validate candidate gadget chains. This means manual inspection is required, which is not only time-consuming but also prone to errors. To address this challenge, we propose a hybrid solution, ODDFuzz, a lower approach to hunting gadget chains automatically. ODDFuzz is comprised of two components, a lightweight static analyzer and a directed Greybox fuzzer. The lightweight static analyzer components use static analyze to discover all possible candidate gadget chains. The directed Greybox fuzzer, on the other hand, utilizes the result from the lightweight static analyzer to generate and mutate the seed. This process verifies whether the candidate gadget chains are both reachable and exploitable. Next, I'll provide a detailed introduction to the design and the implementation of these two components. Let's start with an example as shown in the code on the slide. This example is a simplified version of a well-known gadget chain. In class A, there is a read object method. It first deserializes the comparator object, then deserialize the values, then use the comparator to compare these values, and store them in the ordered array list in sequence. The comparator class has two subclasses, value comparator and the invoke comparator. If a tag can control the comparator and set it to an object of invoke comparator class, they can control the code execution flow and execute the invoke method, achieving remote code execution. From a static analyzer perspective, if we want to discover such a gadget chain, we need to perform time analysis and construct the core graph on the fly. The construction of a core graph on the fly and the time analysis essentially boils down to a point-to-analyze problem. Therefore, we primarily focus on the following 5 types of pointing affecting statements. As you can see on the slide, there are new statements, assign statements, store statements, load statements, and call statements. The commonly used point-to-analyze algorithm in the industry is the classic Anderson-style analysis. However, based on the actual situation of deserialization gadget chain discovery, we have made a variant and simplification of the Anderson-style analysis, which I will detail then when discussing specific aspects. Overall, we implement lightweight static analyzer through a simplified PAG, SPAG, and worklist algorithm. Next, I will use this example to explain the entire process in detail. First, we handle new, assign, store, and load statement. We generate a simplified PAG, SPAG based on these statements. What's the difference between SPAG and the PAG? In the SPAG, we don't introduce the concept of object. This is mainly for 2 reasons. Firstly, Java deserialization gadget chains are too long. Introducing objects would lead to greater memory usage, computation space, and time consumption, potentially preventing the analyzer from being complete within the reasonable given time. Secondly, in this part, we allow for false positives. We treat the left and the right value of these 4 types of statement as a vertex in the SPAG, and use a directed edge to connect the right value to the left value, because the object pointed to by the right value flows into the left value. This completes the construct of the SPAG. Let's generate the SPAG graph for this example according to the rules mentioned above. The SPAG graph for this example is shown in the figure 1. Next, we perform timed propagation on the SPAG graph. We use the widely used worklist algorithm to propagate timed in SPAG graph. For example here, if allocate 1 is tainted, the taint will propagate along the edges in the SPAG graph, make X also tainted. Additionally, there is an implicit propagation. If X is tainted, then X.F is also tainted. We use the traditional worklist algorithm to perform timed propagation analysis. Once the propagation stops, we process to handle the call statement. There are 3 common types of calls in Java language: static calls, special calls, and virtual calls. Static calls and special calls has a single target method that is determined at compile time, and it can be obtained through static analysis. On the other hand, the target method of the virtual call is determined at runtime and can have multiple possibilities. This greatly expands the size of the call graph and increase the potential for discovering deserialization gadget chains. Hence, we will focus on handling virtual calls. For virtual calls, we perform class hierarchy analyze (CHA) on the call statement only when the receive object is tainted. In the context of Java deserialization, most of the time, if X is tainted, the attacker can fully control X and specify the target method of the call statement. The CHA algorithm aims to cover all available gadget chains that can be exploited by abusing Java runtime polymorphism. However, we perform CHA only when the receive object is tainted to efficiently prevent the path explorer issue. In addition, we also have a pure knowledge to handle certain specific methods, such as the native method in the JDK and the specific methods like a read object. We only needed to know that the attacker can fully control the return value of the read object method. By utilizing these technicals, we can handle all call statements. As more functions call are proceed, more edges and loads will be added to SPAG graph. For example, in the code on the slide, if the object pointed to by X can flow to R, an edge from X to R will be added to the SPAG. At this point, because of the addition of the new loads and the gadget and the edges, the healthy time propagation can resume. When all method calls have been proceeded, the worklist algorithm terminates and the complete call graph is generated. Next, we search for the sync method in the call graph and output all paths that reach the sync method. Each path from a source method to a sync method represents a gadget chain. Now, we have a complete understanding of how lightweight static analyzer works. Let's return to our previous example. As I mentioned earlier, the read object method is handled specifically, and its return value is marked as tainted. Therefore, when the call statement invoking read object is proceed, this stored comparator is marked as tainted. Next, the taint propagates along the edge of the SPAG, and the comparator is also marked as tainted. At this point, the taint propagation in the SPAG halts. All vertices in the SPAG are tainted. And then method calls are proceed. And when the call statement comparator.compare is encountered, the receive object comparator is tainted. Hence, class hierarchy analyze is performed. And the comparator has two subclasses, invoke comparator and value comparator. The compare method are added to the call graph. From the code on the slide, we can see that the compare method of invoke comparator happens to call the sync method.invoke, which forms a deserialization gadget chain. Now, we have a complete understanding of the design and the implementation of the lightweight static analyzer, and I'll highlight a few key points about it. Firstly, the goal of the lightweight static analyzer is to locate all candidate gadget chains within limited computation time and resources, while minimizing false negatives and tolerating some false positives. We propose a variant of the Anderson-style analyzer as a solution and employ two techniques, SPAG and on-demand CHA, to achieve this goal. The use of SPAG helps reduce computation time and memory usage, while on-demand CHA helps minimize false negatives. The lightweight static analyzer generates many candidate gadget chains, and the ODDFuzz validate these candidate gadget chains to mitigate false positive by performing direct Greybox fuzzing. ODDFuzz constructs the serialization byte stream as a seed based on the candidate gadget chains, and uses fuzzing technology to verify whether these gadget chains are reachable and exploitable. Fuzzing technology is not commonly practiced in object-oriented language, especially when it comes to validating deserialization gadget chains. During the usage of fuzzing technology, we encountered several challenges. In the following, I will provide a detailed explanation of these challenges and how we addressed them. The first challenge lies in generating seeds that conform to the Java deserialization data format, as shown in the slide. The Java serialization byte stream is a sequence of bytes consists of fields with various meanings. Generating and mutating seeds based on this format can make the entire problem extremely complex. However, looking at it from another perspective, our goal is not to fuzzing deserialization mechanism itself. We can approach this problem differently by constructing an object and then serialize it, rather than generating a serialization byte stream. This way, we transform the problem into how to generate an arbitrary instance we want. Fortunately, Java provides a powerful introspection mechanism that can help us achieve this goal. First, we instant an instance through sum.miss.unsafe. Why don't we call the constructor directly to instance the object? Because some classes do not have low argument constructor, and calling the constructor may cause some side effects. As for the field of the class, we set them through reflection. In this way, we have a universal method for constructing the arbitrary instance we want. From the code in the slide, we can see that in order to invoke the compare method of invoke comparator, the comparator in class A should be set to an instance of the invoke comparator class, and the method name and the class name in the invoke comparator class should be set to appropriate value. This forms a multi-level tree structure, and we use a property tree to represent this structure. The root node of the property tree represents a class object that holds one or more gadgets, and the leaf node represents a series of class fields that contains the field type and the name. We instant each class involved in the gadget chains to construct the property tree. Specifically, if the property type of a leaf node is an object represented by another property tree, we merge the two property tree by connecting this leaf node to the root node of another property tree. After that, we implement the seed generating and mutating by assigning and mutating the values of its leaf node. The value of a leaf node in the property tree could be set to pre-generated values or random generated value. The pre-generated values are generated based on the candidate gadget chains. During the mutation, these pre-generated values have a higher priority. The table on the right side of the slide showcases the candidate values that can be assigned to the leaf node. The first column represents the type of the leaf node, and the second column represents its candidate value. For classes involved in candidate gadget chains, such as a comparator, the values are generated based on the gadget chain. For example, the candidate value for the comparator is the instance of the invoke comparator class. For string type, we include the class name and the method name involved in the candidate gadget chain, as well as some special values and random strings. For integer type, we prioritize the integer close to 0. For object type, all the aforementioned values are considered. As different candidate values are assigned to the result, seeds are generated and mutated. To efficiently select and schedule seeds, we propose a feedback-driven seed prioritization approach. In this scenario, the Gadget chain suggests that the expected execution flow is indicated by the grayed out basic block in the control flow graph. We utilize seed distance to evaluate the quality of seeds, while good seeds cover more grayed out basic block and have a shorter seed distance to the target basic block. And within this method, we aim for the seed to trigger more branches in the gadget. Therefore, we also take code coverage as a feedback matrix into account. With the equation shown in the slide, the fuzzer can determine the number of mutation chances to be applied to the current seed, and evaluate whether the mutated seed should be favored. This strikes a balance between exploring devices execution paths and prioritizing a seed that is more likely to reach the sync method. In this part, I would like to emphasize some key points about the directed Greybox fuzzer. The goal is to verify whether the candidate gadget chain is reachable and exploitable. By applying a series of tactics like a property tree and hybrid feedback, we have successfully adapted fuzzing technology to object-oriented language and achieve the goal.
Hi, I'm Howard. We evaluate ODDFuzz from different perspectives. We select Y source reveal a collection of 34 known gadget chains discovered in 22 common Java libraries that can be exploited to perform on-seed deserialization. In addition, we also apply ODDFuzz on 4 famous Java applications to test its ability. As shown in this table, ODDFuzz identified a total of 20 out of 34 known gadget chains and dynamically generated a sync-reachable seed for 16 out of these chains without false positives. The remaining 14 gadget chains are missed by ODDFuzz in static identification stage, mainly due to the limited support for certain dynamic features of Java language, such as reflective calls and dynamic proxy. Compared to Gadget Inspector and C Hybrid, ODDFuzz reported 16 gadget chains without false positives. By contrast, the number of truly exploitable gadget chains reported by Gadget Inspector and C Hybrid is 3 and 2. Among these chains, we find that ODDFuzz can detect certain unique gadget chains that cannot be found by baselines. When applied to real-world applications, ODDFuzz successfully detects 6 previously unknown gadget chains. 5 of them have been assigned CVE IDs. And in this part, I will analyze a real-world gadget chains in WebLogic discovered by ODDFuzz. In the slide, we can see a candidate gadget chain that was discovered by the lightweight static analyzer. The first hop of this gadget chain converts Java deserialization into coherence custom deserialization. Coherence deserialization is similar to native Java deserialization, and it also executes magic method during deserialization, such as read external. Therefore, all read external method can serve as source method for the gadget chain. The sync method in this case is a known security-sensitive method that executes MVL expressions. The candidate gadget chain suggests that the read external method of partial result will call this add method at line 8. And then in the add method, the compare method will be invoked at line 4. And then in the compare method of extract comparator, the extract method will be called, which eventually leads to the invocation of the mwill execute expression method. ODDFuzz constructs a property tree based on this gadget chain. As shown in this slide, after seed generation in the multiple rounds of mutation, ODDFuzz select suitable seed. These values in property tree are pre-generated based on the gadget chain. These values are random generated, while the final values that involve the execution of the sync method are hard-coded. When analyzing the execution of the aforementioned seed, we discovered that the actual stack trace differs slightly from the candidate's gadget chain, as shown in Figure 2. How does this happen? In line 4 of the read external method, a tree map instance is constructed, and its comparator is set to the injected extractor comparator object, which leads to the premature invocation of the sync method. In other words, the seed generated by ODDFuzz triggers the method earlier than expected. Since the sync method have already executed, the seed distance is 0, and ODDFuzz reports this gadget chain finally. In the second part of this talk, I discussed several challenges faced by existing solutions. Does ODDFuzz address these challenges? Firstly, ODDFuzz partially addresses them by combining a lightweight static analyzer with a directed Greybox fuzzer, significantly improving both precision and recall. Additionally, ODDFuzz provides the ability to automatically validate gadget chains. However, ODDFuzz still has some limitations that can be addressed as future work. Firstly, the static analyzer of ODDFuzz is relatively coarse and will not be sound in some scenarios. Secondly, ODDFuzz needs to support more dynamic features such as reflection and dynamic proxy, especially since dynamic proxy are common in Java deserialization gadget chains. Lastly, the seeds generated by ODDFuzz are not the final exploits. Exploring method to automatically generate the final exploit can also be considered as future work. In conclusion, this talk provides the following takeaways. First, attendees will know the current state and the remaining challenge of state-of-the-art gadget chain discovery tools. Second, attendees will understand how ODDFuzz works and why it handles gadget chains efficiently and preciously. And last, attendees will know how to optimize fuzzing when adapting it to an object-oriented language. Thank you. If you have any questions, please contact us via Twitter.